Okay, so do I need to repeat the last statement about the De Bruijn sequences or no? Do you understand the algorithm to finding? No? Okay, so I just briefly explain what happened in the ending of last lecture. We were discussing the De Bruijn sequences, and we proved that the algorithm 1, 0 is better than 1, 1 better than 0, or 1 prefer 0 works. And so by this algorithm, I mean that we want to find the sequence that contain all key subsequences of zeros and ones, and these subsequences is meet exactly once. And so if we want to provide this algorithm, so I suppose that last time it was 0 better than 1, but we can also write similar algorithm. If 1 is better than 0, you just need to start with n zeros, and then try to write the root 1 if possible, and if the sequences will be repeating, then we'll write zeros. So for example, if we start with 4 zeros, then we wrote 4 ones. The new ones is not good because we have subsequences on 4 ones will be repeated, will repeat. So we wrote 0, then 2 ones, because 3 ones will be again, we already have zeros and 3 ones. Then we have 0, 1, 0, 1, 0, 0, 1, 0, 0, 0, 1, no, 0, 0, 0, something like this. So we need to provide all sequences of length 4. It means that we have 4, 8, 12, 16, 22 elements. Without the last elements, it will be, so we have 4, 8, 12, 16, 12, 21 elements. And so we'll have every possible subsequence of length 4 in our sequence, yeah? Maybe, maybe, because the length will need to be 19, so I think there will two, I think we can cut this off, yeah. Something like this, or maybe, so, let me check again. So we wrote here 0, then we have 1 and 1, and third one we can't write. Then we have 0, then we can have 1 because we don't have 1, 1, 0. Oh, okay, we already have 0, 0, 1, 1, so we can use this one, yeah? So we wrote 0, then 1 because we don't have 1, 0, 1, 1. Then we wrote, yeah, this is not correct. 1 because we don't have, yeah, 0 here, then 0, 0, 1, 0, 1, 0, 0, 1 we don't have, 1, 0, 1, 0, 1, 0, 1, 1 we already have, so we wrote here 0, and then we add again 0 and 0, something like this, yes, 12, yeah, so now we have exactly 19. Okay, and we proved that this algorithm working using the properties of the De Bruijn graph. So if you want to prove that this algorithm is going to write the De Bruijn sequence, I just wrote the corresponding tree. So this tree will be sounds rather big, but so I need to, but I need to route like 8 vertices, and I connect them with the edges which will correspond to this for thicknesses of length 4. I will have and I wrote different edges. The one edge is when we add the element 1. So here, for example, we have 0, 0, 0, 1. And the other edges will be green. 1, 1, 1, 1. 1, 1, 0, 1. 0, 1, 0, 1. Okay, so last element can be 3 ones. 1, 0, 1, 1. Okay, and I forget about the here 1, 0, 0, 1. Here we have 0, 1, 0, 0, 1, 1. And that's 1, 2, 3, 4, 5, 6, 7, 8. Okay. And for the green edges, I will have all zeros, 1 and all zeros. 1, 1, 0 is 0, 1, 1, 0, and 1, 1, 1, 0. For 0, 1, 0, I will have 0, 0, 1, 0, and 1, 0, 1, 0. Yeah, and for this one, I will have 0, 1, 0, 0, and 1, 1, 0, 0. And so we see that red edges and green edges are all formed 3. And so if I start with 4 zeros, so I started with this one, and then every time I will prefer, so I will first wrote red edges and green edge. And then it is easy to see that if I start, I must finish in the same node because my graph is order graph. And so I finished with this green edge 0, 0, 1, 0. So this is the last edge. This is the first. And then I prove by induction that I use all the edges to go through, because if I use this green edge, this means that I was twice in this node. So I used all the edges out of this node. And this means that if I use these green edges, this means that the same holds for these two nodes. So if I use the green edge, this means that I meet this vertex twice. So if I use the green edge, this means that I already was here twice. And so, but green edges are forming a tree. So if so it's just by induction, because if I have green tree and green means that if I walk out with green edge, that means I walk through every edge in this vertex, in this vertex. So if I use this edge, that means that I use these edges. If I go through these edges, that means I use these edges. So by induction, I can prove that I visit every green edge, but every green edge means that I use also every red edge, because the red edge are also used before green. So I go out from every vertex, so it means that I was at white, so I use all the edges. And so the same idea will be proven it if I have more than 2 elements. So if I have 3 elements, the same idea holds, because I have an order in elements. So I say that, say for example, that 2 prefer 1 prefer 0 also works, because if I use the edge, the edge which corresponding to the edge number 2, which means that I 0, which means that I already use all the edges using 1 and 2, and so if I go out using 0, that means that I use all edges, and so by induction the same property holds. But there is not the unique algorithm to get in the De Bruijn sequences, and so in tests and homeworks maybe we'll be presenting some different algorithms for getting the De Bruijn sequences. Okay, do you have any questions about it? About this? Yeah. Sorry? Yes. Yes. How that colors the edges? Yeah, it's very simple. So if I add 0 at the end, it means that they're green, and if adding 1 at the end, it's red. It's just like this algorithm. So 1 prefers 0 means that I use red then green. So I just so I start here, then I go through red edge, then I use red edge here, then I use red edge here, and you see that I will be getting my sequence here. So I start with 4 zeros, then it will be 0, 0, 1, it's this edge, then it will be 0, 0, 1, 1, which is this edge, then 0, 1, 1, 1, which is this edge, and so I go through all the red edges and this one, and so now I use all red edges, and so I need to use green. So I use green edge, admit here, then I need to use red here, then I can use red, but again I use already red here, then I use green, and I already use red and I use green, then I use red here, and I already use red, then I use green, and so then I use red, green, and then this one. So I just walk through every edge using this algorithm. Okay. I don't know if this border working or not. Okay, let's continue, and our next topic will be Hamiltonian graphs. Hamiltonian graphs. So it's a similar topic to the Euler graphs, but so when we're talking about Euler circuit or trail, we want to cover all edges within our root. Either it's closed root within its circuit, or it's not closed, it's trail. But I use terms circuit and trail because I can meet one vertex twice when I cover all the edges, because I can come into the same vertex many times. So Hamiltonian is similar conception, but now I want to cover all nodes or vertices. Cover all vertices. And when I need to cover all vertices, I bothered about using exactly cycle or path. So I don't want to meet one vertex twice. So I want to, so as in here, I want to cover all edges, but I want to go through each edges only once. Same code here. So I want to cover all vertices, but I want to go through each vertex only once. So I need to talk about cycles or path. So cycle, I mean that here we have sequences of vertices and edge, such that all vertices are distinct, and so of course all edges are distinct, and the edges EG is connecting the pair EG and VG plus 1, and the same holds for EN. So EN is connected to VN with V1. If I want to with a cycle, and if I talk about path, then I just forget about this last edge. So a graph G is Hamiltonian if it has Hamiltonian cycle. So by Hamiltonian cycle, I mean cycle that goes through each vertex or graph. A cycle which go through every vertex of G. And so we again is in we can talk about Hamiltonian cycles and Hamiltonian paths, and we want to have a criterion to graph to be Hamiltonian. But this problem is more complicated than previous two problems. So when we're talking about planar graphs or Euler graphs, we have the exactly criterion. So for Euler graphs, we have the Kuratowski theorem about subgraph homeomorphic to K3 or K33 or K5. When talking about Euler graphs, we just need to calculate the degree of every vertex. But now there is no good criterion to graph to be Hamiltonian. And this problem is somehow connected to the root problem. So I don't know if it's the sorry. Yeah, it's like a routing problem, root problem. So it's one of the famous combinatorial optimization problems, which means that you have map and you have some cities and you want to, so you know the distance between cities, so we have like some graph and edges, and on the edges we can write numbers which correspond to the distance between the cities in miles or kilometers. So we have like here some numbers are given. And the question is, we want to go through all the cities with minimal number, with minimal root, and minimal root is just the sum of all numbers of the edges which we used in our root. Yeah. So it's known that this problem is non-polynomial problem. So we don't have any good algorithm to find the minimal root. By minimal, there is some different similar questions. Either we want to go from one vertex to another with minimal root, or we just want to go through all the cities with minimal, which when the sum of the edges will be minimal. But all this problem, so we can assume that our graph is complete. So we have all edges between every cities, and we have like different. So we just can route any possible route from vertex to vertex. But this algorithm have exponential growth depending on the number of vertices here. So we have many minimal roots, many roots, and so its problem is not very simple. But our problem is similar. We need suppose we have just now all edges are we have weight 1, and we want to go through all the edges. But additionally, we want to and minimal root here corresponds to so we cannot meet any vertex, so we cannot use any edge twice, and so it's similar problem, not quite this problem, but similar problem. Maybe you think that it is connected to the number of edges in our graph, but the simplest Hamiltonian graph is just cycle, and it have n edges. So if we have n vertices, of course we have cycle. So the lowest bound for graph to be Hamiltonian is just have to have n edges. And of course, if we have the maximal number is complete graph Kn, which have of course many different Hamiltonian cycles. So for example, this one or this one. So exactly, we can just have every order of the vertices will be obtaining the cycle will be Hamiltonian. So so the edges must be between n and n times n minus 1 over 2. But of course, if we have many edges, so if we have the big number of edges, then we can guarantee that our graph is Hamiltonian. But of course, this is will be not just n edges, because of course if we have n edges, then so there are plenty of examples where we can have Hamiltonian cycle. So the question is, can we somehow so what is the lowest bound of number of edges where we can guarantee that our graph is Hamiltonian? So suppose we have graph G with n vertices, and so can we just route some estimate number of edges, so f of n edges, to be guaranteed that we have Hamiltonian cycle, or maybe path. So of course, if we have the n needs to be minimal, as low as possible. So of course, if we have n times n minus 1 over 2 edges, then we can guarantee that we have Hamiltonian cycle. But can we so how can we get lowest so lower function, maybe minimal, guaranteed number of edges, that we have Hamiltonian cycle or path. But maybe we'll start with examples. And I will just provide you some examples, and you try to find, do this graph have a Hamiltonian cycle or no. So let me just okay, so we start the usual example. Which is not very simple, but maybe so it's called maybe I will write some other graphs. So in each of these graphs, you need to find if there exists Hamiltonian cycle or Hamiltonian path. So is this graph Hamiltonian? Okay, so maybe I will write some different pictures so you to just try. This is cube. We just take the edges of the cube. Okay, so maybe I'll write another example. So the question is how to prove that. So can we have some Yeah, so can we have some, how can we provide a proof if graph is not Hamiltonian? Okay, so I think we'll have like, we will break like 5 minutes, and then we will continue discussing the problem. And try to solve it.
If I start, I will come back here, okay? So basically, for example, I should do what here and then somewhere here and I should, if I do this kind of thing, it won't be Hamiltonian.
Sorry? So maybe the last one. So this two I think is simple. Yes? Because we can, so the last one is very simple, we just can take and draw this circle. Yeah, cycle. And I think the middle one is also not very hard. Yeah, because we can just go like this. Yeah, but what about the first one?
First one also.
I think it's not very hard to provide the path covering all the vertices.
First one. We start from the upper one and then go left, down, right, up, and then center. Again. No. Left. Make it exposed.
Yes.
And then oh.
Okay, so you got the path, so you have path, but you now you can pretend cycle. This way. Yeah, but how can we prove that this graph is not Hamiltonian? Yeah, so can you, so I know, so maybe it's not very easy to see that this graph is not Hamiltonian, but okay, maybe we can just so we want to prove that we cannot provide a cycle here, but maybe we can just use some properties. So can you just say what do you know about this graph? What are the properties of this graph? Yeah, so first of all, every vertex have a degree 3. Okay. Which means that if we assume that we have a Hamiltonian cycle, that means that we will use so we will use 10 edges and 5 edges will be left. So each of the vertex will have degree 1. So if we cut out our cycle, then the remaining graph every vertex will have degree exactly 1. Okay, so what about what you can say about cycles in this graph? Sorry? How many? So what cycles can we have in this graph? Can we have cycles? So what is the minimal number of nodes in cycle in our graph? 5. Yes, so we have no 3 cycles and no 4 cycles here, yes? We cannot have we don't have triangles and we don't have 4 cycles here because for each 2 vertices on the outer pentagon, if we take 2 adjacent vertices, then the connected vertices are not adjacent. So we can't have 4 cycle here. And for cycle, we need to have 2 edges on the 2 vertices on the border and 2 vertices inside pentagon. So we have no 3 cycles and no 4 cycles. Okay, so the minimal number of edges in cycle is 5. So the question is, can we? So suppose we have Hamiltonian cycle, then we have. So let's draw the cycle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we draw this Hamiltonian cycle, and then we need to draw. Oh, sorry, I have one more vertex here. Okay. So we need to provide additional 5. So we need to draw additional 5 edges such that, first of all, every vertex will have degree 1, and second, there will be no 3 cycles or 4 cycles. So for example, so if we draw edge from the node 1, so with which vertex can we connect to this node, this vertex 1? If we have no 3 cycles and 4 cycles. So we cannot provide it. So 2 already use this edge. 3 will have triangle. 4 will have cycle 4. So we cannot connect 1 with 5 or 6 or 7, yes? 5 or 7 is symmetrical, so we can just take the two possibilities. First of all, we want, so for example, we have this edge. Okay, can we connect? Let's take the next node, for example, 2. Can we connect it to any other node such that there are no cycles of length 3 or 4? Okay, so we cannot connect it to the yeah, I just want to consider not many cases, so maybe we'll just yeah, so it's better. Oh no. Yeah, so it's better consider not maybe node 2 but node 6. So let's look at the node number 6 here. So it cannot connect to the 7, 8, 5, 4, 3, and 9 because we will have the cycle of length 3 or 4. If we connected it with 1, we'll have triangle. If we connect with 10, we'll have cycle length 4, and if we connect with 2, we'll also have cycle length 4. So we cannot connect this vertex 6 to any of the vertices in this graph. Yeah. So this proves that we cannot have this edge 1, 5. So another option is that we have connected. So again, let me draw some. Picture 1, 2, 3, 4, 5, 6, 7, 9, 10, and so 1 connected to 6. Can this happen? So I just can, if I can use the previous case, then it's easy to see that if so the only option I have is that the vertex is connected to the opposite vertex. And this must be holding for every of these vertices, but if it happens, then I will have cycle of length 4 here. And so again, it is not, it cannot be happening because our graph has no 4 cycles. So for example, the node number 2 can be connected to the 8 because we already consider this case here. So vertex can be connected only with opposite. So you see that this graph is not very hard. So it has only 10 vertices and 15 edges. But to prove that it has no Hamiltonian cycle, we need to consider some cases. So if you have problems with such simple cases, it's then it shows that even for simple case we have troubles. So of course we have troubles for arbitrary case. But if we return to our question, for example, can we just say about how minimal edges do we need to be guaranteed that we have a Hamiltonian cycle? Okay, so can you, if we return to this question, can you provide an example with many, with as much edges as we can imagine, but we have no Hamiltonian cycle? So can we just draw a graph with no Hamiltonian cycle, but the number of edges is big enough. So it's just similar to the number of edges in the complete graph. So in complete graph we have like n times n minus 1 over 2. So could you just provide an example when we have like similar number to this, but which have no Hamiltonian cycle? So it's if I said something about complete graphs, then you can imagine that we have Kn, complete graph on and vertices, and so how many vertices do I need to cut off of this graph such that it will have no Hamiltonian cycle? So I need to get rid of some edges. What is a simpler example that will have no Hamiltonian cycle? Maybe someone has any ideas on what we can do with this. Yeah, so maybe we'll make a I don't know, we can just start with 6 vertices. So how many edges can be cut from the K6 such that it will have no Hamiltonian cycle? 4? Which edges do you need to cut off? Yeah, so the simplest idea is just take one vertex and then we have 5 edges coming from it, and then we just cut 4 of them. And we will left with many edges, but we will not have Hamiltonian cycle because if we need to provide a Hamiltonian cycle, we need to all vertices have to have a degree at least 2, and now we have this vertex of degree 1, and so we cannot draw a Hamiltonian cycle. So if you do this with a complete graph Kn, we see that we just need to get rid of n minus 1 edges. So we just take arbitrary node and then delete all edges except for one. And so this graph will be not Hamiltonian, but it will have, just like not n minus 2 here. So we'll have how can we? Yeah, so we can just write something like this formula. So we have complete graph on n minus 1 vertices plus 1 edge. And this is similar to the n squared over 2. So we can just get rid of n minus 2 vertices, and we already have a graph which is not Hamiltonian. So the formula for Fn is my question. So Fn must be strictly bigger than n minus 1, n minus 2 plus 1. So the next question is, can we guarantee that our graph will be Hamiltonian if we have edges more than z? So if we have more or equal than n minus 1, n minus 2 over 2 plus 2 edges, do we have a Hamiltonian cycle? So and the answer is yes, and to prove it, we prove some similar propositions, theorems. Theorem 1 and theorem 2. So first is the we need to be always mistaken these two. So first is Euler's theorem and second is Dirac's theorem. And the first states that if G is graph on n vertices, and we have for each two, so n must be more or equal than 3, and for each two non-adjust vertices we'll have then the sum of the degrees is more or equal than n. Then D is Hamiltonian. So if for every non-adjust vertices we have the sum of the degrees is more or equal than n, then G is Hamiltonian. And Dirac's theorem is simpler. So if G is graph on n vertices, n is more or equal than 3, n for all vertices has degree more or equal than n over 2, then G is Hamiltonian. So the second is similar to the first, but it is simply to check because you just look at all degrees, and if all degrees is more or equal than n over 2, then it's Hamiltonian. All right. Strictly more than n. Yeah, one moment. Okay, so first of all, we can prove, if we prove the Euler theorem, then we prove Dirk's theorem, yes? So we can just is it correct? Yeah? So if we know that for any non-adjust vertices, the sum of the degrees is more or greater than n, then we can prove this one. Because, so let's check this property. So if we have, two vertices, the degrees is more or equal than n over 2, so the sum of the degrees is more or greater than n. So this will be holding, despite of the adjustment or not adjustment. So for all Vn W, we will have the sum of the degrees is more or equal than n, and so by the Euler theorem we will have the graph G is Hamiltonian. Okay, that's first remark. Second remark that we'll already discuss the counterexample. So counterexample, the biggest counterexample that we can provide is Kn without, so we have one vertex n connected to the, for example, vertex 1, and we have here Kn minus 1. So this is the simplest examples with many edges, but non-Hamiltonian. And so in this graph, if we take two non-adjacent vertices, so for example n and 2, we have that this vertex has degree 1, and this vertex has degree n minus 2. Yes, so the sum of the degrees will be n minus 1, and this will be not holding this criterion. So we have, so we cannot wrote here n minus 1. So for n minus 1, we have a counterexample here. We already discussed that we have no Hamiltonian cycle here, and so we can for each n we can provide an example where this is not holding. So this is exactly the minimal number of estimated number of edges that we can wrote here. So we can wrote here n minus 1. Okay, so we prove. So we now don't need to prove all these two theorems. We just need to prove the first theorem, and it contained like 2 steps. So now we have. Let's prove this theorem. So suppose I have a graph G on n vertices, and we know that for every 2 non-connected vertices, we have this condition. So we're doing this in 2 steps. First of all, we assume that we need to prove that we can construct maximal path, and then we prove that it is actually a cycle. So let's talk something about some property about what we have. Suppose we take, maybe not we, let A1, maybe not, V1, E1, V2, E2, etc. Vk be the path of maximal length in G. So we have V1, V2, V3, etc. Vk, and this is the path to maximal length, so we don't have the path of length k plus 1. So we have exactly 2 options here. So if we have an edge between V1 and Vk, so we now have a cycle here. Or we don't have edge between V1 and Vk. Which of these two properties are true? So either this situation are true or this situation are true. Can we just say something about it? Can we just so if so let's look, for example, in this situation. What does it mean that we have a cycle on V1, V2, etc., Vk, and V1, Vk be the path of maximal length? This means that if we have any vertex outside of our cycle, first of all, we cannot connect it. We cannot have an edge connected to the omega, because if we have an edge that going outside our cycle, then we'll have the path of length k plus 1. Yes, so if we have any edge here coming out of our cycle to any of the vertices, then we can have a path of length k plus 1. So this means that if this path is maximal length and we have here a cycle, this means that this cycle is not connected to any other vertex. But of course, our graph should be connected, because if we have, now we take this omega and take any vertex from our cycle, the sum of the degrees is more or greater than n, which means that they have a common neighbor. Yes? So if we have, so this property actually means that if we have two non-adjust vertices, and so we can, if we look at edges that coming out of V and double V, that we have at least one common vertex here, because the sum of the degrees is more or greater than n. And so we have, here we have n minus 2 vertices, and a sum of them is already greater than or equal than n. So that means that we have, for each omega non-adjacent to V1, we have common vertex here, which contradicts that with this path for the maximal length. So if V1 and Vk is connected, that means that we already found the Hamiltonian cycle here. Maybe I need this to be rich. So if there exists an edge between V1 and Vk, then if k is not less than n, then there exists omega which is connected with Vi, I is from 1 to k, and then we have path Vi plus 1, Vi plus 2, etc. Vi, Vk, V1, etc. Vi, W, contradiction to the statement that V1, Vk is path of maximal length. Yeah, but so this, so if k is less than n, then this is the WS which is connected with Vi, because our graph is connected. But I just explained this from this property. Our graph is connected. G is connected because any two non-adjacent vertices have common neighbor. So each two non-adjacent vertices has common neighbor, which means our graph is connected, and by the connectedness we obtain that. So if V1 and Vk is connected, then we already find the Hamiltonian cycle. So now we just need to look at situation where there are not adjacent vertices. Okay. So part 2. So we have found a maximal path. And we know that V1 and Vk are not non-adjacent. So we have no edge between them. So first of all, V1 and Vk cannot be connected to the vertices outside this path. So if some of them have edge outside this path, so for example, Vk has connected with some W, then we have path of this was not path of maximal length. That means that V1 and Vk has no neighbors outside set V1 and set Vk. So the picture is like this. V1 is connected with some of the vertices here, and Vk is also connected to some of the vertices here. And we also know that some of the degrees, so we know that degree of V1 plus degree of Vk is greater or equal than n. So how can, what can we say about the neighbors? So let me ask you the question. So if we have some edges here, then maybe we can construct a cycle. And if we can construct a cycle of length k, and we can use the previous So we can use previous idea here. So if we somehow construct a cycle with this vertex, then we can use previous case and prove that we have Hamiltonian cycle. But so when we have a cycle here, we will have a cycle if something like this happened. If V1 is connected with some vertex Vj, and Vk is connected with vertex Vj minus 1. Because if this happens, then we can construct a cycle going like this. From V1 to Vj minus 1, then to Vk, then to Vj, and then to V1 again. So if there exists an edge of V1, Vj, and Vj minus 1, we have such edges, then there exists a cycle V1, Vj minus 1, Vk, Vk minus 1, etc., Vj, V1. And so we can use the previous case, so we can construct a cycle from maximal path. And so again, we will have that since the graph is connected, then some vertex will connect to the cycle, and so we can construct a path of this path will not the maximal length because we can construct a path of length k plus 1. And so graph G will be Hamiltonian. So all we need to do is prove that we can find some G such that G minus 1 with K and 1 with G will be edges. So we have edges of V minus 1 with G and Vj minus 1 with K. And I just want to be sure that if I have this inequality here, that from this I can prove that there exists some G such that these two are edges. Just from this, just from the proposition that they have the sum of the degrees is more or equal than n. But I think it's just like Pigeon principle, because if you just wrote that, yeah, because if you just look at the numbers of elements which is connected with V1, so for example, we just write that so we just wrote the set A will be such G from 2 to K minus 1, such that V1 Vj is an edge, and B will be set of G from 1 to 2 from 2 to K minus 1, such that Vj minus 1 Vk is edge. maybe I need to write this until k. I don't know. Maybe I should write until k here. Yeah, so the number of elements in A is will be degrees in V1. Number of elements in B is degree of Vk, because V1 and Vk connect only with this vertices. And so the number of elements in A and B is more than equal than n, but each of these elements in the set are not greater than k minus 1, which is not greater than n minus 1, which just means that they have intersection. So they are yeah, but maybe I need to use some lower bound here. So just if I knew that number of elements in A and B is greater than n, yeah, so I need just wrote here, yeah. Yeah, okay, so do you understand how to prove it? Or is it just hard to understand? So, I just need to prove this simple idea that if I just denoted all the ends of edges of V1 and then shifted them by -1, then I will exactly meet one of the ends of the edge from Vk. This is just from this one, because the number of edges going from V1 plus number of edges going from Vk will be intersecting into this element. Yeah, but maybe I write here that number of elements of A union with B is not greater than n minus 1. then if the intersection will be empty, then the number of elements of A and B will be equal to number of elements of A plus number of elements in B, and this is more than greater than n, and this is not greater than n minus 1. And so there's contradiction. So I just proved that they have something in common. And so we have this property holds that if we have, so there exists some G such that V1 and Vg is edge from E and Vk is edge, and so we can just construct the cycle and solve the proof that G is Hamiltonian. Okay. I think now we will have a break, like I don't know, 10-15 minutes, maybe 20 minutes, and then I will just try to make some remarks about this theorem, and then we will be test until the end of the seminar. Okay. So if you have any questions, you can ask me now, because maybe I just rush some things. I know, talk about 5 minutes and then we can just have a test. We'll finish. So, the last question that we have. So we just prove Euler's theorem, and so we can prove the Dirac theorem. So can we obtain from this theorem that our previous statement that if we have more than n minus 1 times n minus 2 over 2 plus 2 edges, then our graph is Hamiltonian. Okay, so maybe we can use Euler or Dirac's theorem to prove this statement. Hamiltonian, yeah. So we already have example which have one less edge which is not Hamiltonian, and we can try to prove that if we add one edge, then our graph G is Hamiltonian. So maybe we just need to prove that, we just need to check that. So first of all, we can look at all cases where n is strictly less than 3, which 1 and 2. So maybe it's not, let's check for example, for n equal 2, it will be. Two edges. Yeah, so we have two vertices and two edges between them. I don't think it's correct example because I think we assume that our graph has no repeated edges, so we just can assume that n is more or equal than 3. Yes, do you have any thoughts? So we just need to check. What do we need to check? We need to take the two nodes, V and W, which have no edge between them, and then check that the sum of the degrees is more or equal than n. This is the ORS theorem for the graph to be Hamiltonian. So can the opposite be true here if you have such number of edges? Yeah, maybe someone has ideas. No? So how to can we calculate? So how many edges do we have here? So how many edges do we need to delete from complete graph to obtain this inequality? So this graph, this means that we have complete graph, and then we delete not more than n minus 2 edges. Yes? Because we already calculate that if we have n minus 3 edges, because this is minus n minus 2 is, so n minus 2 minus n minus 1 is n minus 1 n minus 2 over 2. So we need to cut off not more than n minus 3 edges from Kn to obtain graph with these edges. So can we delete not greater than n minus 3 edges to obtain two vertices which sum of degrees will be less than n? Because usual vertex, so if you take vertex in Kn, each of these vertices will have the degree n minus 1. So we cut off the edge which connected them. So if we delete the edge which connected them, then we connect, so the degrees will be n minus 2, as sum of the degrees will be 2n minus 4. And so to get this, we need to cut at least n minus 4 edges. Yes? And plus the edge between them will be exactly n minus 3 edges. So something like here, we need to delete. So we need to see if the statement can be correct if the so we need to delete strictly more than n minus 4 edges, which means that we have delete strictly more than n minus 3 edges, but this contradiction is this inequality. Yeah, I think it's okay because so if you want to check this inequality, we need to delete many more than n minus 3 edges. So for example, if we have like k10, then we have so degree of v will be 9, degree of w will be 9, and then we need to cut off one edge between them, and then sum of the edge such that the sum of the degrees will be lesser than 10. But now sum of the degrees is 8 plus 8, 16. So we need to cut off this one plus 6 more edges. So we need to cut off more than 7 edges, but we already have gotten not more than 7 edges. So this is contradiction, which proves that this graph is Hamiltonian. So we find the estimate number of edges. So we find the minimal number of edges to be guaranteed that the graph is Hamiltonian. We already checked that if we take so we have a graph which have one less edge which is not Hamiltonian, and with these edges we can prove that graph G is Hamiltonian. But this is not very pleasant estimate number, because this is similar to n squared over 2. And if we take arbitrary graph, then I think we can have much lesser edges of graph in general to be Hamiltonian. But we don't have, so there are some different criteria for graph G to be Hamiltonian, and I think it's called Theorem of Erdős and Hvatel. But maybe I'm a mistake. It is about the independent number and the connectivity number. But I don't think that the theorem is rather hard, but I don't think we have time to prove it. And so the next time we will move to some external problems on graphs, which we discussed in Telegram. And now having the same number of vertices, and the edge is just complement to all possible pairs of vertices. Yeah. So just we have, so edge is just the subset of B times C, and but here we assume that we subtract the diagonal, and so we delete all the edges in our graph and draw all the edges that we don't have in our graph.